Hello and welcome to my lab report. I'm Robert Pegg, and today we will be discussing Lab 5, which is about Faraday's Law. For this lab, I had to perform an experiment where I would drop a magnet through a tube of aluminum foil and measure how long it would take for the magnet to hit the table. Upon repeating this process 5 times, I got an average value of 0.305 seconds. After that, I analyzed the experiment and created a computational model using fundamental physics properties like Faraday's Law, the Biot-Savart Law, and Newton's laws of motion. Later, we will discuss further the usage of these principles. Then, after creating the model, I compared my observations and my predictions, with my model predicting a 0.3-second time for the magnet to travel through the tube. The structure of the rest of this lab report is going to be as so. First, I will talk about setting up the lab. Then I will talk about the results. From there, I will use the results to create the model. After that, I will answer some interesting questions, and then some final thoughts and conclusions. For this lab, I needed the following materials. By recording a video of the magnet falling through the tube, I can see accurately when the magnet will hit the table. Along with that measurement, I also needed to measure the length, width, and radius of the foil. Here are the results of my lab. After dropping the magnet 5 times, I got an average value of 0.304 seconds to travel through the tube. Along with measuring time, I also gathered the length, width, and radius of the foil, as well as some important values for the magnet, which I got from my Lab 3. And now to discuss how I created the model. Firstly, I modeled the tube as a series of rings. Then I can calculate the magnetic field at each position relative to the magnet. From there, I can calculate the charge of magnetic flux for each ring caused by the magnet. Then, by using Faraday's law, I can calculate the induced current in each ring. We can extrapolate the force from this induced current using the Biot-Savart law. We can relate the force on each ring to the force on the magnet by using Newton's third. From there, all we need to do is calculate the net force by including gravity, and then we can use Newton's second to update position and velocity, finishing our model of the magnets falling. Here is the code. This is not all of the code, just the important bits. As you can see, I plugged in the constants for my measurements, and then created two functions, one for calculating the magnetic field, and the other for calculating d flux dt. By combining these, using the process detailed on the previous slide, I can model the falling magnet. Here are the results of the computational model. The video on the right is a loop of the magnet falling through the tube. As you can see, it falls quite quickly, which matches up with my model's prediction of a 0.3-second travel time for the magnet through the tube, which is very similar to my observation, which resulted in an average time of 0.305 seconds. Some possible reasons for the slight difference is the lack of error resistance in the model and the human error present in the measuring of the time. Also shown is the velocity time graph, which shows that the tube has an effect because instead of accelerating only due to gravity, its velocity nearly levels off due to the effect of the tube. And now for some interesting questions. The first question is, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Ohm's law says that by decreasing the resistivity, the induced charge would increase, meaning the time for the magnet to fall would increase. The second question is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes or slits would decrease the induced current because there would be less material to magnetically oppose the magnet falling. Less induced current means the magnet would fall faster than with a complete tube. Now for some final thoughts and conclusions. I had a good time doing this lab. I think programming the model helped with my understanding of the principles governing magnetism and current. Thanks for watching.